So, we will go through the next 4 assignments. Thus, assignment number 5 mechanistic analysis with 2-step reaction, assignment number 6 on the mechanistic analysis with EAR reaction, and the next assignment on catalytic reaction, and the last assignment number 8 on Warburg impedance. So, in the assignment number 5, first question is, we have an elementary reaction, metal 2 plus in solution depositing and becoming metal atom. It takes 2 electrons, the Faraday current density that is given by one of these 4 choices. So, this reaction you can write the reaction rate as K1, concentration of metal 2 plus solution minus K minus 1, and of course, it is just metal which has an activity of 1. 2 electrons are involved in this. So, it is going to be K1 M2 plus solution minus K minus 1, all these terms within the parenthesis multiplied by 2. This gives the rate, and if you multiply that by Faraday constant, you would get the current. Okay. This in fact should remain as metal 2 plus solution. D is the correct choice. Next question is, in that reaction, if you are given the rate constant values K10, B1, B minus 1, and the concentration of metal 2 plus solution is 25 millimolar. First question is, what is the value of K minus 10? So, we have to remember at DC potential of 0 with respect to equilibrium potential, we expect the current to be 0. So, you cannot arbitrarily choose the value of K10 and K minus 10 for a given concentration of M2 plus solution. So, this is given in terms of 10 power minus 9 moles per square centimeter per second. Then the next question is, at a DC potential of 0.3 volt with respect to equilibrium potential, what is the magnitude of cathodic current density and what is the magnitude of anodic current density? While doing the calculation, we should remember that 1 mole is 1 moles per liter, and when you convert that to moles per centimeter cube, it becomes 0.001 moles per centimeter cube. The answers that we expect are 2.5 multiplied by 10 power minus 9 moles per square centimeter per second. Then for the cathodic current density, we expect it to be somewhere between 0.9 to 1.1, and for the anodic current density, we expect it to be close to 97 milliamp per centimeter square. So, we know the expression for the current, and at the DC potential of 0, we will write K1 is K10 exponential B1 EDC, and when DC potential is 0, this is just going to be K10, and similarly K minus 1 is going to be K minus 10 at E equal to 0 volt versus equilibrium. Therefore, you can substitute here and then show that K minus 10 is going to be 2.5 10 power minus 9 appropriate units. To calculate the cathodic current density, see this reaction is cathodic reaction and the reverse reaction is anodic reaction. K minus 10 exponential B minus 1 EDC for a given DC potential. At 0.3 you would get certain values and multiply by Faraday constant, you get 1. In fact, there is a correction here, this has to be actually 2 because you have 2 electron transfer. And likewise, anodic current density is the rate of reaction multiplied by 2F. So, there is a correction here which would come close to 194 milliamps per square centimeter. If we have a simple electron transfer reaction and assuming mass transfer is rapid, that means kinetics are rate limiting, then the Faraday impedance of this system can be modeled as a simple resistor or as a capacitor in parallel with the resistor or in series with the resistor. Of course, Faraday impedance can be modeled as a simple resistor. It is independent of frequency. So, we should select choice A. Next question is, when you have metal going into metal plus adsorbed plus electron, and in the second step metal adsorbed goes into solution, how would we write the fractional surface coverage of this intermediate species? You are given 4 choices. For this we have to write gamma d theta by dt. So, this reaction forward reaction forms the species M plus adsorbed, reverse reaction consumes it, second reaction also consumes it. So, we should write gamma d theta by dt k1 1 minus theta minus k minus 1 theta minus k2 theta. B is the correct choice. And if you have chosen that equation correctly, you can naturally get the steady state fractional surface coverage by setting this to 0. When potential E is EDC, this is set to 0, and you can rearrange and show that the fractional surface coverage under steady state condition is given by C. And what is the Faraday current in this? First reaction, forward reaction k1 1 minus theta minus k minus 1 theta. First reaction, forward and reverse reactions involve electron transfer. The second reaction does not involve any electron transfer. So, we will have to choose F k1 1 minus theta minus k minus 1 theta as the correct equation. Next question is, what is the expression for d theta by dE? We know the mass balance equation. Okay. We have to expand this in Taylor series. And we know that we can expand the left hand side as gamma j omega d theta by dE EAC. Right hand side, of course, you have to expand in Taylor series. Each term you have to expand in Taylor series. And truncate. And then rearrange this equation. Eventually, you would get B1 K1 dC minus B minus 1 K minus 1 dC in the numerator, and K1 dC, K minus 1 dC, and K2 is of course independent of potential in the denominator. So, we should select A. Then the next question is, what is the Faraday impedance for this reaction? Okay. We know the Faraday current. The current expression is given here. Here we have to expand this in Taylor series, truncate it, and then we would get the following terms: B1 K1 dC 1 minus theta SS minus B minus 1 K minus 1 dC theta SS for expansions in K1 and K minus 1. The expansion in theta would give us an expression in d theta by dE, and that is going to be minus K1 So, C is the correct choice for this question. Next assignment, in the EAR reaction, that is electron transfer, electroadsorption, first reaction is electron transfer, second reaction is EAR. You are given that the kinetic parameters K10 is 10 power minus 5 centimeters per second, B1 is 20 volts inverse, K20 is 10 power minus 6, B2 is certain number, K minus 20 is 10 power minus 6 moles per centimeter squares per second, B2 is 20 volts inverse. Solution species concentration, P in solution, Q in solution, and A minus in solution, they are all at 100 millimolars. At a DC potential of 0.25 volts measured with respect to the equilibrium potential, what is the fractional surface coverage of A adsorbed? Okay. The answer is going to be close to 0.572. How do we get this value? First we write the mass balance equation, gamma d theta by dt. First reaction does not change surface coverage of A adsorbed. Second reaction, forward reaction produces it, reverse reaction consumes it. So, I will write K2 1 minus theta multiplied by the concentration of A minus in solution minus K minus 2 theta, and this you can rearrange and show the fractional surface coverage theta SS is given by the expression here K2 dC multiplied by concentration of A minus in solution. In the denominator you have K2 dC A minus solution plus K minus 2 dC, and with the pre-exponent values and the exponent values and the concentration given at the DC potential, the value of K1, K2 and K minus 2 are about 1.48 10 power minus 3 centimeters per second. K2 is also 1.48, but it is 10 power minus 4 centimeters per second, and K minus 2 is 1.48 10 power minus 8 moles per centimeter square per second. Note the units carefully, and we have 100 millimolar, that is 100 and we also remember 1 mole per liter is 0.001 moles per centimeter cube. So, accounting for this, you can substitute in this expression and you can get a value of close to 0.572. And at that potential, what is the total Faraday current? Now, the first step contributes to the current, the second forward reaction as well as the reverse reaction contribute to the current. So, the total current is given by K1 P solution 1 minus theta. This is the first step, this is the second step forward reaction, this is the second step reverse reaction. Get the algebraic sum, substitute for these values and you would get close to 6 milliamps per centimeter square. And at that DC potential, if we acquire AS, what would be the charge transfer resistance and what would be the polarization resistance? In order to get these values, we have to get the expression for impedance. Okay. In order to get the impedance value, you have to first write the mass balance equation, expand that in Taylor series and then rearrange to get d theta by dE. We have already seen the mass balance equation, right. If you expand this in Taylor series, you are going to get j omega gamma d theta by dE EAC on the left hand side. Concentration of A minus solution, we assume that it remains a constant. Okay. K2 and K minus 2, of course, we are going to write it as K2 dC 1 plus B2 EAC, and likewise K minus 2 we write it as K minus 2 dC 1 plus B minus 2 EAC. This is an approximation. And after rearranging, you can show that d theta by dE can be given by the expression shown here, that is B2 K2 dC concentration of A minus in solution 1 minus theta SS minus B minus 2 K minus 2 dC theta SS, all these terms come in the numerator. In the denominator, we have K2 dC A minus solution plus K minus 2 dC plus j omega gamma. After getting the value of d theta by dE, we have to take the current equation and expand that in Taylor series. When you expand that in Taylor series, you are going to get K1 dC 1 plus B1 EAC, concentration of P in solution remains a constant, or at least that is our assumption, multiplied by 1 minus theta SS minus d theta by dE EAC. This is for the first term, and likewise you can write for the second term and the third term, and when you rearrange it, you would find that you can write that as a DC component plus an AC component. Okay. The AC component, when you group them, you are going to get B1 K1 P solution 1 minus theta. So, it is going to be B1 multiplied by this term, B2 multiplied by this term evaluated at a constant DC potential, and that corresponds to a constant theta, that is theta SS, and you are also going to get minus B minus 2 K minus 2 theta SS, and that is going to have terms without d theta by dE. The terms with d theta by dE are grouped, and you are going to get K1 DC P solution plus K2 DC A minus solution plus K minus 2 DC, and for d theta by dE we have to substitute from the equation that we derived before. You can rearrange this, you have I EAC, you can divide the IFAC by EAC and you would get Faradaic admittance, that is equal to inverse of Faradaic impedance. So, you get an expression like this. Now, when omega tends to infinity, when the frequency tends to infinity, the Faradaic impedance is going to be the charge transfer resistance, and when frequency tends to 0, whatever Faradaic impedance we get is the polarization resistance. When frequency tends to infinity, d theta by dE tends to 0. So, charge transfer resistance is going to be given by this expression without d theta by dE. So, I am just taking the expression on the first line, and you would get a value close to 6.85 ohm centimeter square. At 0 frequency, you can simplify d theta by dE to some extent. Omega tends to 0, this will go away, and you can substitute for these values and calculate the Faradaic impedance. That is essentially going to be polarization resistance. Main point to note here is that it is a negative value. Okay. So, that means impedance spectrum is in complex plane plot is going to look like this. Charge transfer resistance is somewhere close to 6 or 7 ohm centimeter square, and polarization resistance is somewhere close to a negative value minus 94 ohm centimeter square. Next question is, the polarization plot of an electrochemical system is given in the graph here. If we take impedance spectrum at EDC of 0.7 volt, somewhere between these 2 points, somewhere around this value, what would happen to the polarization resistance? What do we expect it to be? Can it be negative? Can it be positive? The slope of this line di by dE is negative. Current decreases with potential here, right. Obviously, that means dE by di is also negative, and polarization resistance value has to be equal to the inverse of the slope of this line. So, polarization resistance will be negative, and in this system, if we take data at 1.2 volts somewhere here, we expect the polarization resistance to be positive because the slope of this line is positive. The next question, we have a 3-step reaction. Metal loses an electron and becomes metal plus adsorbed. Metal plus adsorbed loses another electron, becomes metal 2 plus solution. I am sorry, metal 2 plus adsorbed, and metal 2 plus adsorbed becomes metal 2 plus solution. First question is very simple question, how many intermediates are there? You have metal plus adsorbed and metal 2 plus adsorbed. So, basically you have 2 intermediate species, and in the kinetic limited regime, that is assuming mass transfer is rapid, how many loops do we expect to see in a complex plane plot? Do we expect to see 1 loop and 2 loops here, maybe 3 loops? We are not differentiating between an inductive loop and a capacitive loop. We will call this as 3 loop, we will call this also as 3 loops. We expect to see 3 loops because 2 adsorbed intermediate species are there, and just based on the charge transfer resistance and double layer capacitance, you are going to have one loop. Each intermediate species can give rise to one time constant, therefore, we have totally 3 loops. Then next question is, if I want to get the kinetic parameter values based on optimization, okay, we get experimental data, use this model and simulate the spectrum, compare the spectra, experimental spectra with the model spectra, and then see if we can match them. At how many DC potentials should we take this data? Now, we have 2 adsorbed intermediates, which means Faraday impedance can be modeled using a circuit like this. This is just for the Faraday impedance. In addition to this, you have double layer capacitance and solution resistance. So, this has 5 electrical elements. Kinetic parameters, we have K10 B1, K20 B2 and K30. In addition, we have gamma. So, we have 6 kinetic parameters which are mapped into 5 electrical circuit elements. So, the ratio 6 by 5, if I round it up, I need to have 6 by 5, round it up, I need to have at least data at 2 different DC potentials. Another example, metal going to metal plus adsorb plus electron, it is a reversible reaction. The second step is a catalytic reaction, metal plus adsorb plus metal gives us metal plus adsorb plus metal plus solution plus an electron. Okay. So, in this we can't just cancel out these 2 species, these species are essential. One metal plus adsorbed is consumed and one metal plus adsorbed is produced by this reaction, but this is a second order reaction. Okay. Now, you are given kinetic parameter values and at a given DC potential of 0.1 volt versus equilibrium, what is the fractional surface coverage of metal plus adsorbed? We expect the value to be close to 0.42. What we do is first write the mass balance equation. The first forward step forms the species metal plus adsorb, the reverse step consumes it, the second step does not consume or produce, okay, it is a catalytic step. So, it does not contribute to the mass balance equation. We can rearrange this and show that theta SS can be written in terms of K1 DC and K minus 1 DC, and at that given potential we can evaluate the value of K1, K minus 1 and K2. We do not need the value of K2, and if you use this expression you can show that theta SS, that is fractional surface coverage under steady state condition, is going to be 0.42. Here how many loops do we expect to see? We have one adsorbed intermediate that is going to correspond to one time constant, and the double layer capacitance with charge transfer resistance will give us one time constant. So, we expect to see 2 time constants at the most. So, we can expect 2 loops, 2 or fewer loops. Now, at the DC potential of 0.1 volt versus equilibrium, what is the Faraday current? Although the second step does not contribute to the mass balance equation, it will produce an electron. The current expression is given by K1 1 minus theta minus K minus 1 theta plus K2, this is given by theta, m is given by 1 minus theta, under steady state condition it is going to be K2 DC theta SS 1 minus theta SS. So, this is a second order reaction. So, you can show that it is going to be close to 0.64 milliamps per centimeter square. Next question, if we use Fromkin isotherm model, we have an expression which says K1 is K10 exponential of beta 1 g theta exponential of B1 e. At what point will this reduce to or simplify to Langmuir isotherm model? When g is 0, the rate constant k will be independent of the fractional surface coverage. In Langmuir isotherm model, the rate constant depends only on the potential and it does not depend on the fractional surface coverage. The Frumkin model will simplify to Langmuir model when the parameter G is 0. Next, without giving the detail, I just described that a mechanism can be described using 15 kinetic parameters, and the mechanism contains 3 adsorbed intermediates. Okay. How many loops do we expect to see? If it contains 3 adsorbed intermediates, we expect to see 4 loops. Each adsorbed intermediate corresponds to a time constant, and then in addition we have charge transfer resistance and double layer capacitance. Now, how many electrical elements are required to model this? We have 3 adsorbed intermediates, which means we have 3 Maxwell pairs or equivalent pairs, and then 1 polarization resistance. So, this is going to be 7 elements, 7 electrical elements are required to model impedance spectrum at a given DC potential. 7 electrical elements are required to model the Faraday impedance of the impedance spectrum, okay, not the double layer capacitance and not the solution resistance. Apart from these double layer capacitance and solution resistance, just the Faraday impedance can be modeled using 3 Maxwell pair. That means it can be modeled using 7 electrical elements. And if I want to map the kinetic parameters to the electrical elements, I need to acquire data at 3 or more DC potentials, because the ratio 15/7 is greater than 2. So, if I acquire data at 1 or 2 DC potentials and model the results using this mechanism, I can have more than one solution, possibly infinite number of solutions. Okay. So, to get confidence in the parameter values, we should have at least 3, preferably more number of DC potentials in which we take data. So far we have assumed that the adsorption isotherm is described by Langmuir adsorption model. If we have a simple reaction, metal going to metal plus adsorbed and metal plus adsorbed going into metal 2 plus solution, but the constants K1 and K2 are described by Frumkin model, Frumkin isotherm, and you are given values K10, B1, G, beta 1, K20, B2 and beta 2, and of course gamma. How many loops do we expect to see in the complex plane plot? We have one adsorbed intermediate, regardless of whether the adsorption isotherm is given by Langmuir model or Frumkin model. One adsorbed intermediate will give rise to one time constant. So, we expect to see maximum 2 loops in the complex plane plot. So, how many electrical elements are needed to model a spectrum acquired at 1 DC potential? We have one adsorbed intermediate, which means Faraday impedance can be modeled by this set of elements. Okay. So, 3 elements are required to model the Faraday impedance of this system. Again, that does not depend on whether the adsorption isotherm is described by Frumkin model or by Langmuir model. Now, if you are going to describe this reaction using Frumkin isotherm model, and if we have to get the parameter values K10, B1, beta 1, etc., by taking the EAS data and using an optimization program, then at how many DC potentials should we take EAS data? Minimum how many DC potentials should we take EAS data? K1 is given by K10 exponential of B1 EDC exponential of B1 G theta. K2 is also given by K20, B2, B2G, gamma. So, the number of kinetic parameters we have is actually 7. The way we have written, B1 and G appear to be independent, but actually you can combine them and write it as one parameter B1G and B2G. Okay. So, we have 3 fitting parameters for K1, 3 fitting parameters for K2, and of course, one parameter gamma. we have a total of 7 kinetic parameters. 7 by 3, when you round it up, that becomes 3. Assignment number 8, first question is, if we have a rotating disk electrode, how does the diffusion layer thickness vary as described by Levitch equation? Of course, if you know the equation, it is pretty straightforward. Delta is given as a function of diffusivity, omega, and the kinematic viscosity nu. So, here it is proportional to omega power minus 1 by 2. So, it is proportional to the inverse of the square root of the rotational speed. Okay. And given a diffusivity value 10 power minus 5 centimeter squares per second, given the kinematic viscosity as 10 power minus 2 centimeter squares per second, estimate the diffusion layer thickness when the RPM is 225 or 1600. Of course, you can substitute the values here in this equation and make sure the units are correct. Then you would get delta value to be close to 33 micron if it is 225 RPM, about 12 micron if it is 1600 RPM. Diffusivity value dA is given as 1e minus 5, nu value is given as 1e minus 2. Of course, rotations per minute, you should convert that to RPS, and you would get delta value by using this formula and convert that to micron, centimeters to micron, by multiplying by 1e4. And when the RPM value is 1600, you can write the same code, change the value of RPM to be 1600. Next, for a simple electron transfer reaction, when we couple mass transfer to the kinetics at the electrode surface, that means we have an electrode surface, we have a boundary layer here, x equal to 0, x equal to delta. At this surface, the coupling between mass transfer and kinetics is given by the equation which relates the flux to the current, the active species flux to the current. The boundary condition at x equal to 0 is actually the flux which is given by dA dou Ca by dou x, and that is going to be equal to Faraday current divided by F divided by N, where N is the number of electrons involved in this reaction. So, we have to select A. Now, consider the reaction A going to B plus electron. So, N equal to 1 here. Initially, the concentration of A and concentration of B are equal, and in the bulk solution they are always maintained equal. When we apply a negative DC bias and a steady state condition, so initially they are equal. Okay. If you apply a negative DC bias, what happens is, when we apply negative DC bias, rate of reverse reaction increases, rate of the forward reaction decreases. That means we will consume more B at the electrode and we will produce more A. When we consume B, concentration of B will decrease. When you produce A, concentration of A will increase, and under steady state condition it is going to look like this. So, on the surface, concentration of A is going to be higher than the concentration of B when the DC potential is negative with respect to open circuit potential. You are given the value of diffusivity dA and dB, they are equal. Concentration of A and B in the bulk are 100 millimolar. K10, K minus 10 values are given, B1 and B minus 1 values are given, and you are given a boundary layer thickness of 10 micron. DC potential is plus 0.1 volts with respect to open circuit potential. You are given the temperature, you are asked to find the concentration of A and B on the surface in millimolar. Now, we have derived this equation which relates the concentration of A on the surface and B on the surface to the parameter values. you have to refer to that equation and then substitute for these individual values. You will find that concentration of A is 4.52 and concentration of B is close to 195. Because it is positive DC bias with respect to open circuit potential, Ca is going to be less than Cb on the surface. So, here is the code. You are given dA, dB, concentration of A in the bulk, B in the bulk, kinetic parameter values. In order to use this equation and get the values correctly, you have to make sure that the units are proper. So, we convert the diffusivities to meter squares per second, concentration also to moles per meter cube. You have to make sure that the units are consistent. Calculate the value of K1 dC, K minus 1 dC, and then write the formula. You can get the value of concentration of A on the surface and concentration of B on the surface. We multiply by 1000 to get moles, because this comes in terms of moles per meter cube. We want to convert that to moles per liter, and you can convert that to millimoles by multiplying by 1/6. If you multiply by 1/3, you will convert to moles. If you multiply by 1/6, you will convert to millimoles. And to calculate the steady state current value is given by F K1 dC Ca on the surface minus K minus 1 dC Cb on the surface. Now, we know the K1 dC value, we know the K minus 1 dC value. We have calculated concentration of A and B on the surface. Substitute in this formula, you will get the Faraday current in amps per meter square. You can convert that to nano amps per centimeter square by multiplying the value by 1/5. So, this is the continuation of the previous code. Then you are also asked what is the charge transfer resistance and what is the polarization resistance. Okay. So, charge transfer resistance is given by the expression here 1 by the terms within the parenthesis F B1 K1 concentration of A on the surface minus B minus 1 K minus 1 concentration of B on the surface. So, you can write it in the formula RT inverse is F B1 K1 CAS minus B minus 1 K minus 1 CBS, and RT is of course inverse of this. Value comes in ohms meter square. You can convert that to ohms centimeter square by multiplying by 1/4. To calculate the RP, we have to first remember that Faraday impedance is given by this expression, and we have to calculate the value when omega tends to 0. What happens to hyperbolic tangent of square root of j omega by dA delta divided by square root of j omega dA, and you can show that that becomes equal to delta by dA. Similarly, the second expression becomes delta by dB. So, this simplifies to delta by dA, this simplifies to delta by dB when omega tends to 0, and then you can substitute for these values, get the value for polarization resistance. So, I have written the expression here. This is actually RT inverse, so you do not have to recalculate it. You can use the expression that was used before. The value comes to be very high. So, instead of expressing that as ohm centimeter square, I had divided that by 1/6 and expressed that as mega ohm centimeter square. Then instead of EDC being 0.1, what if EDC is 0 voltage? You can rerun the code setting EDC to be 0, and you would find that the value of polarization resistance is close to 0.55 mega ohm centimeter square, and charge transfer resistance is close to 2.7 kilo ohm centimeter square. Now, instead of finite boundary layer thickness, if we use semi infinite boundary layer thickness, what do we expect to see for the charge transfer resistance, and what do we expect to see for the polarization resistance? Charge transfer resistance, you can calculate it easily. Polarization resistance, it is going to be infinity, because the complex plane plot is going to go like this, and it is never going to reach the real axis. Another way of saying that is it is going to reach the real axis at infinity. Then you are also asked, at a given frequency 100 hertz, that is a finite frequency, what is the real value and the imaginary value for the Faraday impedance. Now, all you have to do is to substitute in this expression and then calculate the real part and the imaginary part. So, the MATLAB code is given here. This assumes that you have copied the other relevant values from the previous code. Frequency is given, you have to first calculate omega, that is angular frequency, and then calculate the value of Faraday impedance. Once you have the Faraday impedance, calculate the real part and the imaginary part.